It's a pleasure to introduce our next speaker for today, Brandon Levin, who will talk about Serre conjectures in higher dimension.
Thanks, Fred. Thanks so much for having me. Great to be here virtually, as much as I would like to be in Montreal right now. But so I'll be talking about Serre conjectures in higher dimensions. Toby advertised a possible discussion of Breuil-Mazard, but I hope you're not too disappointed that I decided to go with the theme of the conference and talk about applications to the Serre conjectures. And in particular, I want to talk, but I will be building on Toby's talk yesterday in the sense that one of the things I really want to highlight is connections to the Emerton-Gee stack. How can we think about how can we use the Emerton-Gee stack in ways to understand the weight part of Serre's conjecture in higher dimension, and especially some questions about the wildly ramified case in higher dimensions. So this is an area that has been studied in limited ways so far, and so that's sort of I'll sort of hope to get to that near the end of the talk. I wanted to begin with some very brief motivation from the classical case. So we'll just begin where I think several talks have begun, which is the sort of Serre's conjecture for modular forms, which I think we've seen this a few times. So we have our two-dimensional continuous odd irreducible representation, and then there exists an eigenform f of some specified prime to p level and minimal weight. And of course, so sort of the weight part of Serre's conjecture, or the Serre weight conjectures, is a question arose out of trying to understand this weight recipe of Serre. So this K of R bar, and understand its generalizations. And I'll soon be getting to those generalizations, but let's just recall one example of Serre's recipe. So this weight K of R bar should depend on the restriction of R bar to the decomposition group at P. So it sort of corresponds to the P part of the P component of this global representation. And so here's kind of a typical example. If I start with take omega bar to be the mod P cyclotomic character, and so let's say the restriction of my R bar to inertia was just an extension of 1 by the cyclotomic to the A. All right, so star is some extension class. And let's assume A is between 0, 1, and P. Then the minimal weight in Serre's recipe is read off from the inertial weight here. So it's A plus 1. And I want to highlight I guess maybe go ahead and jump to what sort of the generalizations look like, which is that we really want to talk about not just sort of minimal weight, but really sort of all weights, all small weights in which you can find your global representation. And so this leads to the notion of, arose again also out of this thinking about mod P companion forms. So the question becomes a question of sort of, are there other weights, small weights, in which you can see your representation? And so we have the following observation. If this extension class is 0, so if you're actually looking at a split, if your R bar is actually split at P, then when you twist, you can twist your global representation by the cyclotomic mod P cyclotomic character. And then if you look at its local factor, we've now sort of scaled away we see that it looks like omega bar to the P minus 1 minus A, trivial. So it sort of appears again to look in that same form as before. All right, and so we see that the minimal weight of this twist of R bar is P minus A. And this is an interesting phenomenon that up to a twist, we see that we actually get 2 forms in small weight in this case, and then there's this, so this leads to the tameness criterion of Gross, where he showed that this weight p minus a form exists, which gives rise to the twist of our bar, if and only if that extension is non-zero. And so this highlights a real theme that becomes, I guess, even increasingly true in higher dimensions, which is that if your factor at p is tame, then you tend to have there's sort of more modular, more small weight forms giving rise to your representation. So in the modern terminology, you would say you have more Serre weights. There's more congruences in that case. And this is an if and only if. So in fact, the other way around is also true, that if you have many congruences between different forms, you can detect whether your local representation is tame, or in this case is split. So in the sort of modern formulation of this twist would be taken care of by adding a determinant factor to your weight. And what you would really say is that your R bar has two modular weights if and only if it's tame. And that's, if you avoid a few special cases, avoids two special cases, that's the general statement. So I'll come back. So in the end, I'll also come back to this tameness criterion and discuss what a similar sort of criterion which holds in higher dimensions. So let's get to our global setup. So I apologize for the onslaught of notation. Very quickly, I should say, the truth is that we'll get to most of our methods are purely local, and so you can essentially, up to some technical hypotheses, everything should hold in other global setups as well. So if you want to work with, unitary Shimura varieties or other sorts of quaternionic Shimura varieties, other sort of options, there's sort of the methods are in a sense purely local, but the easiest from the point of view of stating theorems is to set us up in the global setup of definite unitary groups. So F is going to be a CM extension, F plus the totally real field. I'll take a unitary group of rank n. We're going to assume that it's definite at all the real places. For technical reasons, the totally real F plus is not Q. We assume our definite unitary group is split at P. So the factor at P will just be, GLN. And we'll have a prime to P level. So U upper P will always denote a prime to P level, open compact of the Adels. G sub F will be the Galois group of F bar over F. And R bar is going to be our global representation. We'll assume to satisfy a conjugate self-dual condition. And then for each place V of dividing P of F plus, we'll choose a place V tilde over it, and we'll set this R bar. We'll define the local factor to be the local factor at that place. So we're going to have these local factors which are indexed by the places of F plus. So now I want to introduce the notion of Serre weight, and we want to talk about what the modular weights are of this R bar. And so these are our coefficients. These are sort of the defined. This is given us the weight is given by a factor at P. So if we have any W, which is a ZP module with an action of U sub P, which is the maximal compact at the places above P. So again, this is assuming our group is split at P. So we're just going to have this. These are our local factors at P. Then we can define a space of algebraic modular forms of level U sub P and weight W. And these are just functions from the double coset space where we would mapping to valued in our weight space W with this, you know, which are sort of equivariant for the UP action. We won't, again, this is mostly set up at this point. But maybe important point to note here is that if you look at this space of, you know, the space of forms, if for example, W is in characteristic P, all right, then W decomposes with respect to the, you know, as a representation of U sub P. And similar, the space of forms will also decompose. And this decomposition will be, you know, respect the Hecke action and so on. And so the fundamental building blocks for the mod P spaces of algebraic forms are given by the irreducible representations of U sub P. And this is what we call Serre weights. So the definition, so a Serre weight is an irreducible mod P representation of the maximal of the U sub P, which is the product over these local factors at factors at P. All right, and it'll be important for our discussion here that in some sense these factors also break up in terms of, you know, a product over places. So any such Serre weight is always a tensor product over the, you know, places dividing P of what I'll call sigma sub V, and where sigma sub V is an irreducible mod P representation of the GLN of the residue field KV of F plus V. This is the residue field there. All right, you have the GLN, I mean, if you have GLN OF plus V, it maps to GLN KV, and the kernel is pro P, and so you end up getting that the irreducibles always correspond to representations of the finite group of Lie type. So these also, our focus will be on these Serre weights. In some sense, you can imagine if you don't want to, you know, you can sort of imagine that you really only have one place above V, and you won't lose any, you know, you won't really lose anything if you just imagine you have one place above V, which is what happened in the, you know, modular forms over Q for GL2Q. But it'll be sort of purely focused on this local factors, these sigma V's. One more remark perhaps worth making is that these sigma V's, they're irreducible representations of the finite group of Lie type, but they also come from algebraic representations, and they have a highest weight theory. So each of these sigma V's will have a highest weight, and that highest weight will play an important role in how you think about these, you know, how you characterize them. So now that we have, so for each of these Serre weights or each of these VPs, we can plug VP into these, we can construct a space of modular forms of weight, of level UP and weight VP, U upper P and weight VP. And we say that R bar is modular essentially if it appears in that space of modular forms. So if we have our R bar and we have our Serre weight, then what does it mean for R bar to be modular of that Serre weight? It means that it should appear in a space of modular forms of that weight. And again, we're gonna, not again, but we're gonna be focused entirely on the weight part. So we're gonna you just sort of allow any possible level at this point. We don't try to in some sense we don't try to optimize the level. So it's just saying it should appear in some space of modular forms where we allow any prime to P level. And this M sub R bar is the sort of maximal ideal of the Hecke algebra, which you associate to R bar. And the object of interest then is going to be the set WR bar, which is the collection of all modular weights. So this so this goes back to what I was saying at the beginning, that, you know, if you think about the Gross's tameness criterion in this setup, you're really saying that the set of modular weights would have size, is going to have size 2 in the tame case, and whereas in the non-split extension case, you would just have 1 Serre weight. So it would just appear in one of these mod P spaces of modular forms. So the aim of the weight part of Serre's conjecture is to describe this W of R bar, and to describe it in a purely local way. We'll always assume, you'll see in all the results, we're always going to assume that W of R bar is non-empty. We're not going to be addressing the question, the deep and difficult question of whether the R bar is modular or not, but rather we're just going to assume R bar is modular, and then the question is, in how many weights can you find it? In how many of these Serre weights spaces can you find it? And what is that? What is the structure of WR bar? First thing you hope for is that you expect that the W of R bar should only depend on those local factors. So it should only depend on the restriction to the decomposition groups at the primes above P. So, so this is what the sort of a prototype for the Serre weight conjecture. So this is what the conjecture should look like in cases where, and in cases where it's known, this is what it looks like. So you assume that R bar is modular, and then you want to say that, and then you want to give a description of WR bar in terms of some weights, set of weights associated to the local representations. So this is saying that there's a description of WR bar which only depends on each local representation. So where this W of R bar should be a collection of irreducible FP bar representations of this finite group of Lie type GLN KV. This is not really a conjecture because I haven't told you what this, I haven't defined this yet, right? So that's why I guess I called it a prototype for a conjecture. So I didn't really literally give you, this is not a conjecture unless I first tell you what this weight set should be. So the next, so let's talk about some candidates for this and cases where it's, so this now converts, I guess, into a purely local question. This becomes a purely local question, which is how do I attach a collection of Serre weights to a local representation at, a local mod P representation of these, such as R bar V. So I'll be going, my statements of, some of the statements of the theorems will be global, but a lot of the work will be local. So we'll sort of have a local setup as well, which is a local setup is I start with a, finite extension of QP and an n-dimensional representation of the Galois group of K. And then we ask the question, how might you define this weight set associated to this local representation? So now there's no reference to the global representation. This should really be a purely local question. And let's begin with two expectations. So one is that the weight set should only, we expect the weight set to only depend on the restriction to inertia. The second, which will, I guess, come out a little bit more when we talk about the wild case, is that the set of weights should be contained in the set of weights for the semi-simplification. Semi-simplification is tame, so this is sort of has the, if you want, we can imagine this sort of has a maximal set of weights. so there's a sort of principle that the set of weights goes up under semi-simplification. Maybe it's also worth mentioning at this point that you can also define the set of weights in terms of Taylor-Wiles patching. So if you have Taylor-Wiles patching, you can patch these spaces of modular forms, and you can just say that. So you say that a row bar is modular if the sort of patched module is non-zero for that weight, and this that sort of goes back to what Toby was talking yesterday. So the weight part of Serre conjecture then becomes a question about some local that can be is a means to study the local nature of patched modules. So the question whether these patched modules are purely local, or it really says something about the support of these patched modules being purely local. All right, before I say, we're going to start talking about some candidates for W of row bar. But first, maybe worth mentioning some of the challenges that you see in higher dimensions. So one of the things that happens for GLN that doesn't happen for GL2 is it's not as if you take an irreducible representation of the finite group of Lie type. It's not, there are many possible ways to lift that weight to characteristic 0, and none of them have simple reductions. So you end up sort of, I guess maybe the clearer way to say it is that these, maybe a clearer way to say it is these spaces of modular forms in higher dimension. If you take this Serre weight here, you can't necessarily lift this to a space of characteristic 0 forms directly. So this VP is a purely mod P is a mod P representation. It doesn't directly lift to characteristic 0. So you know a lot more about forms in characteristic 0. And one of the challenges in higher dimension is that you have to choose different lifts or different characteristic 0 things which have this in its reduction, and sort of study them, study it that way rather than directly lifting to characteristic 0. All right, so let's get more into the purely local setup. So when we look at weights, for simplicity, let's say it's unramified. Some of these, let's assume K over QP is unramified. Some of these weight sets are defined in the ramified case, but some are not. So we'll focus on the unramified case. For more detail, I would the G. Herzig Sept article on general Serre weight conjectures has a great overview of all the sort of different weight sets you can associate to a row bar, and how they're intertwined or related, which ones are equivalent to the other ones, under what conditions. So it's a sort of extensive discussion. But I guess the first principle, or the first set, the crystalline weights, crystalline Lifts weights. So this is just defined via Piatek-Hodge theory conditions. So as I was saying earlier, the Serre weights have highest weight vectors, and so you can say that you can define this set here by saying that if you have a crystalline lift in some particular set of Hodge-Tate weights, then you assign the Serre weight whose highest weight is a shift of those Hodge-Tate weights. So and this W-Chris arose, I think, in the initial generalizations. I won't probably be able to name all the people, but Buzzard, Diamond, Jarvis as early generalizations, and then G and Sheen, and then G, Liu, and Sept studied it. And I'm probably missing some other people, but for GL2, this was a very successful. I mean, this really works, and this was the weight part of Serre's conjecture is proved in almost all cases for GL2. And using this crystalline weight set. One of the nice things about GL2 is that you only need to know about the weights. So for n equals 2, you only need to know about sort of Hodge-Tate weights between 0 and p. Whereas for higher weights, you really have to know about, you would really have to sort of make sense of this crystalline's Lifts thing, you'd have to study the weights between 0 and n, and I guess n minus 1p. We know a lot more when rho bar is tame. When rho bar is tame, we have a notion of, so there's a subset of the crystalline weights, which we call the obvious weights. Obvious weights are, the idea is if you have a tame rho bar, then you can write it, then you can define obvious crystalline lifts if you have a crystalline lift, which is essentially an induction of characters. Maybe I'm simplifying a little bit, but for example, if your rho bar was completely reducible, if it's just a completely reducible, then you can ask for crystalline lifts, which are also completely reducible. And this is an easy sort of combinatorial exercise to figure out what those are. And this defines a set, which we call the set of obvious weights. For rho bar, so the best conjecture we have for in higher dimensions is the first big conjecture we really had for arbitrary dimension was if rho bar is tame and generic. Herzig defined W, what he calls W question mark. I'll say more about that in a second, and this is defined using modular representation theory. There is no unconditional conjecture for wildly ramified representations for an arbitrary dimension. So I'll talk a little bit about what we know later, but there is no unconditional conjecture. It's worth mentioning that if you do assume the Breuil-Mazard conjecture, then G. Herzig-Savas introduced this W. Breuil-Mazard, which I guess probably goes back to also G and Kissen. And there they define the, but here you have to actually assume the Breuil-Mazard conjecture, but then you can define a set which works for any rho bar and which you would expect to be the correct weight set if you assume, if you believe all the modularity conjectures. So in some sense, you have a candidate, but you don't know much about it, and you have to assume that you've proven the Breuil-Mazard conjecture first. So let me say a few words about Herzig's set, how it, just to give you a sort of flavor for what it looks like. So the point is that if rho bar is tame, then it has a combinatorial description. So if you look at rho bar restricted to inertia, then it'll be a direct sum. Then it's a product of characters, right? So it's a product over characters, which you can write as a product over the sort of fundamental characters to some power. So you can express the restriction to inertia as in terms of these fundamental tame characters with some exponents. For some niveau f. All right, and then because it's but then you also have an action of Frobenius on these characters. So because it extends to the Galois group, so you really have an action of Frobenius which permutes these characters, and so you can extract from this set here. You can extract from this an element of Sn. And these theta i's, which are this theta, which is some weights. And then using that combinatorial data, you can associate also, this combinatorial data also gives you rise to a Deligne-Lustig representation. So call it RSS. And this was Florian's recipe. So you take you can define tame elements have a combinatorial description, you can associate to them Deligne-Lustig representations. And then how do you get a weight set out of that? Well, these Deligne-Lustig representations are irreducible characteristic zero representations of, these are irreducible characteristic zero representations of GLN K in general. I should say, maybe I'm making some assumption here. So assume that these characters are sufficiently regular, then these are irreducible characteristic zero representations. And you can reduce the mod P. And so he defines W question mark rho bar essentially to be, you reduce these representations mod P, take this collection of Jordan-Holder factors, and then you imply this kind of strange involution. This is an involution on the set of Serre weights. So it's an involution on the set of all Serre weights. And this is how he defines W question mark. So these Deligne-Lustig representations, reducing the mod P, had been studied by the modular representation theory. In particular, Janssen has a formula for how these decompose mod P. And if theta is sufficiently regular, then these sort of have pretty uniform behavior in the sense that the size of this set of Jordan-Holder factors is the same for any, so for sort of independent of the setup. And I'll often refer, as was previously mentioned, we had this generic genericity condition. So the genericity condition is a condition on theta. It's a kind of regularity, P regularity condition on theta, which I'm not going to say too much more about. To give you some sense of the, yeah, so I just say that this W question mark grows in complexity quite rapidly. So if you go to say like n equals 5, this already has something like 1,500 or on the order of 1,500 elements in it. And the only cases, yeah, so it really grows quite rapidly, the set of weights. So now I can state our main result, which appears in this recent preprint with Daniel Lee, Bao Lihang, and Stefano Mora on local models. It's called Local Models for Galois Deformation Rings. So as an application of our theory of local models, we prove Herzig's conjecture under strong genericity hypotheses. So we assume that R bar is modular and satisfies some Taylor-Wiles conditions, and assume that the local factor here is tame and sufficiently generic for all V dividing P. Then we show that the weight set is exactly given by Florian's recipe. This is the first such result in dimension greater than 3. We previously proved the conjecture for dimension 3. So I won't be able to say much here about the sufficient genericity, but luckily the paper is now available. And in fact, I believe if you go even in the first maybe, I'm not sure, certainly in the first 5 pages, there is a discussion of genericity because it's rather a delicate thing here in the sense that we use a lot of, genericity comes from a lot of algebraic geometry that goes into it. And so it's not so easy to make it precise. I would expect that Florian's conjecture, that Herzig's conjecture holds under milder genericity conditions than what we prove. What we do in that paper is, you can think of it as, in a way, maybe one way to think of it is that we study the local geometry of the Emerton-Gee stack. And so maybe it turns out there's a way to, we end up formulating a version of the conjecture in terms of the Emerton-Gee stack, which sort of Florian's recipe then comes out of that formulation. So I want to mention how you can think about I want to discuss the connections to the Emerton-Gee stack. So I won't need to say too much about the stack, but let's just say we have our K finite. Then we have this formal stack, which has its FP bar points are exactly the isomorphism classes. Let's see. So we have this stack. Its FP bar points are exactly the isomorphism classes of n-dimensional representations. You can think of its points. It sort of has these. It sees all the row bars. And Toby hinted at this yesterday, which is maybe he only said it directly for n equals 2, but the irreducible components of the underlying reduced stack are in bijection with Serre weights for GLNK. So there's a natural way to label components by Serre weights. And I'll denote this labeling by sigma goes to C sigma. And I'll just tell you what the characterizing property of this with the limited time I have. All right, let's assume, so let's for simplicity, let's just assume K is equal to QP. Okay, so then we have, if my Serre weight sigma has highest weight lambda, so lambda is equal to lambda 1 up to lambda n, is the highest weight. Then the component C sigma is characterized by the fact that a generic point on that component, this is generic in the sense of algebraic geometry, not in the other sense of generic. A generic point has the property that when you restrict to inertia, it's sort of maximally, well, and then Toby said this yesterday, it's sort of maximally non-split ordinary. And the characters along the diagonal are given by the weights of this highest weight representation up to a shift. So I'm gonna hopefully not get this, hopefully I have this right this time, but it should be, so the last one should be lambda 1 minus n minus 1. Lambda 1 minus n minus 1. So it has this shift in it. And then it's maximally non-split in the graph. And there's some subtlety around Po-ramifié, tri-ramifié issues, which I won't mention here. But now, in any case, you do get a bijection on these things, and this is true and and so this allows us to define a weight set which doesn't depend on, which sort of has no assumptions. Namely, I can just define the set of components that row bar lies on. And this is, I think this is implicit, though maybe not actually spelled out this way in, this notation is never actually established in the Emerton-Gee paper, but we can define a collection of what we call geometric weights, which is just what components does my row bar lie on. Now, this is not a simple set. As I think Toby emphasized several times yesterday, the closure relations, the specialization relations are extremely complicated. So, and it's really quite hard. I mean, yeah, the specialization relations are quite complicated, but nevertheless, at least it's a recipe that makes sense for any row bar. All right, and so I would certainly expect that this set would be contained in whatever. So, I mean, by W row bar, I mean whatever the right weight, whatever the right recipe is. This set of geometric weights should certainly be a subset of it. And in fact, the set of weights, the set of geometric weights should determine the set W row bar. It's a little stronger. So I think the set of Serre weights that you would attach to any given representation should only depend on which components it lies on. And this really comes from the Breuil-Mazard philosophy, that if you can define if you can prove the Breuil-Mazard conjecture on the EG stack, so then then you would get a bunch of cycles, which would then determine so then you end up seeing that the weights would only depend on the components that it lies on. So now, having introduced that, let me say a little bit about the proof of Herzig's conjecture. I'm not going to be able to go into any details here because I also want to be able to talk about the wildly ramified case. So there's essentially 4 steps. The first step, weight elimination, we give a bound, just sort of give an upper bound on the set of possible modular weights. And this was done in earlier work of myself with Daniel Lee and Bao Lehang. And to do that, essentially, we have to give a bound on potentially crystalline lifts of these local representations. And so and some combinatorics that essentially gives me an upper bound on this. Remember, the theorem here is a tame and sufficiently generic. Then there's a second step, which is not, which I want to highlight because it comes up later, which is we also proved in this weight elimination article, we also proved the modularity of these obvious weights that I talked about. So this is sort of, in some sense, this is a starting point. You need to know that you have enough modular weights to get started. I'll say something. I want to go through these steps. I'll say something about that. The big input to the main or the most difficult part of this is this theory of local models, which allows us to say something about the geometry of potentially crystalline deformation rings with Hodge-Tate weights n-1, n-2, 0, and plus the Taylor-Wiles method. So this is essentially, we prove using these local models, this is where the strong genericity comes in. We prove some modularity lifting statements, and we get from this that the geometric weights are contained in the set of modular weights. And then the rather interesting thing that we weren't sure would be true at the time was that it turns out that the geometric weight set, in fact, is the same as Florian's recipe for the tame rho bars. So again, we're in the tame setting here now. So the tame rho bars, you have a geometric weight set, and Florian gave this representation theoretic criterion, and it turns out that those two are in fact the same. And this also follows from studying from local models. We actually relate the components of the Emerton-Gee stack to something related to an affine Springer fiber. And then it turns out this W question mark arises in the study of affine Springer fibers. And so we use the recent PhD of, add this, of Alvarez. Okay, let me write this better. So this equality here uses some work of Alvarez on affine Springer fibers. So the nice thing about the obvious weights in the tame setting, oh, sorry. I switched it around. Thanks. So one of the reasons why you need them, so maybe it's worth mentioning something else that happens in the higher dimensional case, which is maybe not, which didn't happen, didn't occur, wasn't an issue in the n equals 2 case, which is that in a lot of these cases, these deformation, we prove nice geometric properties of these deformation rings, but we can't show that the things are potentially diagonalizable. So for those, this may be a technical for the experts, but most of the lifts we construct are not in any obvious, we're not visible to us, and it doesn't seem likely that they're really potentially diagonalizable. And so you can't just apply change of weight methods of Barnett, Lamb, G, Garrity, Taylor, and other things to these deformation rings. So you have to sort of have you have to have other ways of, I guess, another starting point. And that's where the obvious weights are more accessible from this perspective, whereas the other weights are not. And so you sort of start with the ones you can, and then you sort of go from there from the others. It's a little vague, but happy to answer questions about that later. So what I want to talk about now is obvious weights in the oh, am I running? Do I have 5 more minutes?
Yeah, 5 is fine.
Yeah, so I want to say something about obvious weights in the wild setting. So this is sort of this part 2 I want to talk about in the wild setting. So in the tame case, the obvious weights are in bijection with the vowel group. This, you can think of this for characters. If you have a completely reducible, every permutation of the characters, you sort of have a way to lift it, and this is there's a natural bijection between those. Whereas, and very short, let me just do the best I can in the time I have left. So if I look at this GL3 example, so say I have this 3-dimensional thing and I have the a non-split extension here, then of those, so the split representation will have 6 obvious weights. Okay, of those 6 weights, only 3 of them will be geometric for this row bar. So this row bar will only lie on 3 of those components. So let me say, so W of G of this row bar intersect the obvious weights of the so the obvious weights of the semi-simplification. This has size 3. So you already see that just having this non-split extension decreases decreases the number of obvious weights that you have, because in some sense you can only use permutations that preserve the ordering between A and B. I don't have time. I wish I could write this all out, but ask me later. But there's an interesting phenomenon here, which Toby mentioned yesterday, that if you take non-split extensions of this form in the Emerton-Gee stack, it sort of has another specialization. Like if you imagine you vary the unramified character and you sort of go off, and in fact, you can, this 2-dimensional corner up here specializes to an irreducible representation. And so there's kind of another specialization. There's something like, which maybe I'll call tau. So this is some induction of omega 2, an evo 2 character of a plus 1 plus p plus 1, direct sum, and then you just don't do anything on the other character. So this is, in some sense, we think of this, yeah. So imagine that in fact, in the Emerton-Gee picture, this non-split extension is connected to this tau here. And it turns out it has 3 obvious weights in common with this irreducible as well. And then the interesting point is that, in fact, of these 3, they overlap in 2. They overlap in 2. And so it turns out there is actually, we define a nice notion of obvious weight where such that this rho bar will actually have 4 obvious weights. The 3 weights up here might be like you might think of these as sort of the ordinary weights. They really have to do with the split rho bar, and they come from ordinary lifts. Whereas this other weight, this 4th weight, is a little bit more mysterious. But nevertheless, we believe it deserves to be called an obvious weight, and it behaves like sort of behaves like the obvious weights. And so in fact, we can define a notion of specialization. So we have a notion of rho bar specializing to a tame inertial type. So tame inertial type is just, you take the tame representation, you restrict it to just restriction to inertia. So this is the restriction of a representation to inertia. And we define a locus inside of the component C sigma, where we say that rho bar lies in that sigma. Actually, let me just go to the let me go all the way to the full slide here, and then stop. Brad?
Is that what you're?
No, sorry, I'm not done. I just want to see the whole thing here.
Got to wrap up quickly then.
Yeah, I'm gonna have. Yeah, so I'm. Let me just say that. So in each component, we define a Zariski open, such that we say that rho bar has that weight, has that as an obvious weight if it lies in that locus. And this locus is related to having different specializations. So sort of for different specializations, sort of stratify this locus in some sense. And so let me just say that this allows us to define a notion of obvious weight, which is sort of geometric in nature. And it's larger than the notion of the sort of ordinary weights that have been considered, for example, in G-Garrity and other situations. And I'll just come back, and then I'll just end by saying that we can prove the modularity of these obvious weights. So this is my last slide here. So if you assume that this is now a theorem about modularity of obvious weights in the wild setting. So if you start with so you assume that you start with an R bar again. We assume that it's modular of an obvious weight, so just some obvious weight, and satisfies the Taylor-Wiles hypotheses, and satisfies a sort of mild genericity hypotheses at the places above P. Then we can show that all the obvious weights defined in this for even for the wildly ramified are contained in W of R bar. So we prove modularity of obvious weights. And then finally, we also have a sort of tameness criterion, which is if you sort of have the same obvious weights as your semi-simplification, which is sort of the maximal possible, then you're automatically tame. So that's what this tameness criterion says. And maybe to say that in the wildly ramified case, you're not able to use the sort of potential diagonalizability arguments that we used in the tame case. So in fact, you really have to understand the structure of these obvious weights in some way that you can say, if I start from one, I can sort of start from knowing the modularity of one and then sort of propagate to all the others. So they really are linked in some way, in which you can pass from one to the other. And so I'm gonna just sort of stop there.
Okay, thank you. Thanks for the very nice talk. And people can clap using the clap button. And raise your hand if you have a question. I see there's already at least one. And just to say that the clap, oh, lots of questions. The clap button didn't seem to work for me, but maybe there are lots of people trying to clap. But okay, so Hee-Jong Lee, I'll unmute you.
Yes.
Go ahead.
Okay, I have two questions. So one is like what is the
Is my
main
screen share gone now?
It's disappeared for me.
Mhm.
Go ahead with your question. And I'll
Okay.
try to fix it.
So what's the main reason like you needed the Emerton-Gee stack instead of just considering the like potentially crystalline deformation ring? And the second question,
in which part, I guess?
like I mean, in order to prove the Serre conjecture for GLM, like why was the main reason like you needed the Emerton-Gee stack as an input? And the second question is, I think, might be related to this, but like in order to use the Taylor-Wiles patching, like you prove the tame deformation, crystalline deformation ring or domain, and like was the could you like explain a little about
How we actually prove that part?
Yes.
Well, that's hard. That's why. That's a long story. I mean, in some sense, I guess I would say the local models, the Emerton-Gee stack is a nice tool to use when we study these. It plays more of a role when we try to prove the Broglie-Mazard conjecture. When we prove the Broglie-Mazard conjecture in these potentially crystalline deformation rings. In some sense, it plays less of a role in just when if you're only interested in the weight part of Serre's conjecture. But nevertheless, it's convenient to use this notion of the sort of W geometric, and that one is well defined for the. I mean that sort of makes use of the Emerton-Gee stack in that way. So the proof that the domain part, and there's sort of many steps here, but we construct these local models built out of the local models of Papassou using a monodromy condition. And then in this local model picture, so these are sort of give Zariski local charts on the Emerton-Gee stack, and when you start with a tame row bar, this corresponds under this local model diagram on the local model. This corresponds to being a T fixed point for a torus action. And so the key thing that comes, the deepest, the thing that we have to prove is that these local models they're unibranch at these torus fixed points. So we should prove that the complete local ring on those local models are domains at the torus fixed points. This is not true anywhere else, or it's not generally true in other places. So this is the special thing about the tame row bars, is that this is a geometric fact about the local models, which and if you want me, I'm happy to say more about how that's proved, but maybe that's enough for now.
See, thank you very much.
Michael, you had a question? Michael Stein?
Yes. So could you please say a bit more about why not all of the modular weights are geometric? Is it just sort of the same phenomenon that you see with weight 2 versus weight p plus 1 in dimension 2, or is there a new
and well, I mean, it's right. So it has to do with the yes. So you mean you already see this for as you say for GL2, that you have things that are weight. Let me just sort of trivial weight Fontaine-Lafay things, which still have the Simpkin sim p minus 1 as a weight as well. So that's the example for GL2. The thing that is new is that in higher dimensions, this doesn't just happen. So starting in dimension 4, this doesn't just happen for sort of that kind of situation. It's not just happening in the Steinberg situation. It's really happening for there are generally entailments or sort of the Broglie-Mazard cycles are not irreducible even for generic weights. So that this really happens in generic situations, even for in starting in dimension 4. In dimension 3, I expect the geometric weights are the correct weight set for even in generic situations. But
thank you.
And Tony Fang?
I was just wondering if you could comment on like what the meaning is of the strict inclusion you said that happens sometimes between the geometric weights.
Which strict inclusion?
Geometric weights and Serre weights.
And Serre weights. I mean, so that's what the question I was just answering. So, like, I mean, the example is that if you have this in GL2, you have a let me see if I get this right. Extension of 1 by cyclotomic. I mean, anything in weight 2 is also appears in weight. Anything with the trivial weight also appears with the sim p minus 1, and it doesn't lie in the sim p minus 1 component. So the sim p minus 1 component is somehow the Tre-Ramapier things. So in GL2 you see it for these kind of Steinberg situations where you have spaces of modular forms. I mean, the patching description of it is that the patch of that Serre weight is supported on multiple components. And so it won't just be, it'll be supported on the component labeled by that weight, but it'll also be supported on other components. And that's why you could have, weights that are not geometric, but are nevertheless still modular of those weights. It's kind of interesting that for the tame representations, they just happen to lie in so many components that they kind of don't, this never happens in the generic situations.
Okay, let's thank Brandon again.